Okay, there are two types of titrations, acid-base titrations. Okay, number one is where you have a strong acid titrated by a strong base. So that would be your strong titration. And I'm going to put it in the same category. It's sort of a subcategory of this one. You could also have a strong base titrated by a strong acid, okay? But it falls in the same category. It's a strong titration. And if you're wondering why I stopped writing at that side of the screen, it's because my little comment section is over on the side there, and it's weird to write underneath it. Okay. Okay. So strong. Our second type, obviously, would be, okay, we could have a weak acid titrated by a strong base. So this is our weak strong. So weak acid titrated by a strong base, or in the same vein, a weak base titrated by a strong acid. Titrated by a strong acid. There we go. So again, weak, strong. So you'll notice that in all of these different kinds, there's at least one thing that is strong. Okay, and that's important because you need something strong. A titration means you have a reaction of one thing with another thing to find out how many moles of that thing are present. And in order to find out how many moles of one thing react with moles of another thing, that reaction has to go to completion. If you have an equilibrium, you're not going to be able to tell how many moles have reacted because not all the moles will react. Some of them will just be sitting there in the reactant still. They won't have bothered reacting. So just going back here, okay, this right here would be an excellent titration reaction. This one would be of a weak acid plus a strong base. Okay. And it is important that in a titration reaction, that reaction go to completion so we can calculate moles that are being neutralized. Ah, why so big? Yeah, there we go. There we go. No, no, we don't. There we go. Okay. Whew, that was painful. Okay, so we're going to call this one A and 1B. We'll call this 2A and 2B. And today we might just get through 1A. Okay? So let's take a look at 1A. That's going to be a strong acid titrated by a strong base. So that's our strong. So what that means is that we have two major pieces of equipment that we use in any titration. We have this long skinny tube, okay, with the little valve there. Do you guys remember what that's called? Yes, that is a burette. If you prefer to spell it with an E-T-T-E, that is also fine. Both are acceptable, okay? And in our burette, we are going to put our strong base. So I'm going to color it blue for base. Okay. So that is a strong base of known concentration. Okay. Now down below, what do we put underneath the burette? What kind of equipment do we put underneath that burette? All right. Yeah, we do put an Erlenmeyer flask underneath. That's the one that looks like this. Okay. And the reason that we like that style of flask is that it prevents splashing, right? If things splash up, they're just going to hit the side of the container and go back down. Now I've drawn all over it. And also it's easy to pick up and swirl. Woo. So we do the drippy, drippy, swirly, swirly with this. Now in our flask, we are going to have some strong acid. Unknown concentration. Okay. And so let's actually put some values on this. In our burette, we have, let's make it a strong base, NaOH. That's our most common one. And let's make it a nice simple concentration. Let's make it 0.100 molar. Okay, so we know that concentration. Down below, we have our strong acid, which has an unknown concentration. Okay, and let's see. We would have had to put this strong acid sample into our flask somehow. Do you guys remember? We actually want to know the volume though, this strong acid. Okay, so this is of a known volume. Can you think of what piece of equipment we would use to deliver this known volume into the flask? Yeah, it's a pipette. Okay. Excellent. Okay, so our pipette, you know, looks like this. Da-da-da-da. And we use our little pipette pump. Here we go. With the little roly-dooey and the little plunger at the top that looks like nothing like a pipette pump, but that's okay. All right, so let's say that down in our flasks, only one of them, we don't know how much molar HCl, but we know that we have 10.00 milliliters. Okay, so the two things that we do know, we know our concentration of the NaOH, and we know the concentration of the HCl. Not the concentration, the volume of the HCl. Okay, and if this were just a regular titration, we would drip the NaOH from our initial volume to our final volume, and we would calculate what our volume was. Okay, so we would find our volume delivered, which would equal the final volume minus the initial volume. And from there, what could we find given the molarity of the NaOH and the volume of the NaOH delivered to the point where the color changes? Yeah, we could find the moles of NaOH. Okay, that would give us the moles of NaOH. What could we use the moles of NaOH to find? Yeah, the concentration of the HCl. First, in order to do that, we would need to find the moles of HCl, and that would be using our mole ratio. Okay, and we would use that and the volume to finally find the concentration of the HCl. Okay, so that's the type of titration that we are used to doing so far. If you feel like you need any practice on that, I can put up a practice sheet just on straightforward, let's find the concentration of the unknown solution. If you feel like you don't need that, don't feel obliged to do it. What we're going to focus on now is we're going to say, I'm going to now graph. Instead of actually just looking for a color change, I'm going to stick a pH meter into my flask. Okay, so we're going to put on a different color. We're going to put a pH meter into the flask. Okay. Yes, please. Need some review. Yeah, okay. I'll put that one up over the weekend. We won't get far enough with the titration curves to do much on it anyway. So like over the weekend, you can just kind of focus on reviewing like titration calculations, okay? So put a pH meter into the flask, and what it's going to do is we are going to measure the pH over time as we add the volume of NaOH added. And so initially in our flask, we have 0 milliliters of NaOH added. And rather than having an unknown concentration of HCl this time, I'm going to make life really simple. I'm going to say I know the concentration, and it is 0.100 molar. Okay? So initially in the flask, what is the only thing that is in the flask to start with? HCl. That's right. Okay? And its concentration is 0.100 molar. So what would our initial pH be? Calculate that for yourself. What would our initial pH be if the only thing in the flask at the start is 0.1 molar HCl? Okay, concentration of H plus would be 0.1, which is the same as 10 to the negative 1. And so the negative log of that whoops, negative log, the negative log of 10 to the negative 1 is 1. All right, so we're going to put our initial pH of 1. Okay. Now, if we have, now one thing I want you to notice about our two solutions here is that for this titration, to make it nice and easy, the concentration of the hydroxide and the concentration of the hydrogen are the same. If we have 10 milliliters of the HCl, what volume will it take of the NaOH to completely neutralize the HCl? I'm going to write that down here. What volume of 0.1 molar NaOH will completely neutralize the 10 milliliters of 0.1 molar HCl? Yeah, because everything is the same concentration. This would give us 1 millimole of HCl, and we would need 1 millimole of NaOH to neutralize that, and so that would be, we would also need 10 milliliters. Okay, we can get more into calculations later, but for the purposes of this, I just wanted to say, okay, we're going to, at 10 milliliters, we're going to have complete neutralization. And if at 10 milliliters we have complete neutralization, all the HCl has been reacted, and we haven't added any excess NaOH, what will our pH be? Oops. Okay. What will the pH be of the solution B when completely neutralized? Yeah, it's going to be pH 7, right? Because we've taken our NaOH and we have reacted it with HCl, and we got NaCl plus H2O. And these guys, when it's completely neutralized, these guys here are going to be all gone. Well, that's not my highlighter. Okay, and so the only thing we will be left with is we'll be left with the salt, NaCl, and water, which both are neutral. Okay, so our pH at that point is neutral. Do you guys remember what we call that point when the reaction is complete and there's no excess of either reactant? That is called, anyone remember the name of that point? It's the something point. The tipping point. That's good. It is a tipping point, but that's not what we call it. It is actually called, and maybe we didn't discuss this before, it is called the equivalence point. Okay? It is also known as, also known as the stoichiometric point. Sounds familiar. Yeah, I've probably mentioned it. We probably just didn't focus on it very much. Okay? So the equivalence point or the stoichiometric point is where there is no excess of either reactant. So when we have gotten to our equivalence point of a strong acid, strong base titration, all of the acid and base are gone, and all we are left with is this neutral solution. And so at the equivalence point of our titration, we are going to have a pH, in this case, of 7. Okay? So at the equivalence point, our pH is going to be 7. Before we get to the equivalence point, we're going to have, we've got all acid down at the beginning. We start adding some base, and I'm just going to show you, the last thing we'll do for today is I'll just show you the general shape of the curve, okay? As we start adding base to our solution, the pH is slowly going to go up. The slope is really shallow though, okay? It's a really, really shallow slope. It doesn't go up very much because we still have lots of excess HCl. And then we get to our equivalence point, which really is a tipping point. It's, what do they call those in math class where you switch directions all of a sudden? Inflection. It's like an inflection point, okay? And it all of a sudden, oh, look, we have neutralized all of our acid. So all of a sudden, we're going to go from being acidic, having a pH less than 7, to going up and having a pH of greater than 7. I've done a terrible job at drawing this. This should actually be longer here. There we go. That looks better somewhat. Okay. And then, now that we've gone into the basic range, it will continue to get a little more basic as we add more hydroxide, but we don't get that great big huge jump in pH as we turn from being acidic to being basic. So if you see this S-shaped curve, okay, that's a titration curve. Okay, and it means that we're starting, we've got acidic, 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 acidic. Oh, I'm all neutralized, and then now I have excess base, excess base, excess base, excess base. Okay, and I think that's where we're going to leave it for today, just because that's gone on for quite some time.